All right, so we're going to go ahead and get started. Today we are going to be talking about Unit 4. We're going to start, or excuse me, Unit 5. Is that right? Let me make sure. Yeah, so we're starting Unit 5 today, which is exciting because that means we only have one more unit. We have this unit, and then we have Unit 6 to cover, and then we'll be done with all of the material that we need to learn for this semester. So you may notice whenever you log on and look at the due dates, it seems like the due date's really far away. I think it's, let's see, the next due date is November the 11th. So yeah, it's almost a month away. But in that time, we have several sections that we need to cover. So we'll be covering 3 sections from Chapter 7, and then we'll cover 4 sections from Chapter 8. This week, we're just going to focus on Chapter 7. And then next week, we'll do half of Chapter 8. And then the following week, we'll do the last half of Chapter 8. So we have this chapter. It's not hard, but the theory behind what we're going to be doing is kind of complicated, but most of the calculations are really easy, and they just involve using a couple of very simple formulas. But like I said, the theory behind what we're doing is kind of complicated, but it's important for us to talk about it because the theory that we learn in this chapter will help us perform calculations that we need to do in Chapter 8 and in Chapter 10. So you're going to see the formulas that we use today, they're going to keep coming back up over and over again as we go through Chapter 7, Chapter 8, and Chapter 10. All right. Before I switch the screen over and get started, I did want to let you know that there seems to be some issue with D2L syncing the grades from Hawks at this time. I had to go in, I manually synced one person's grades, and it took about 20 or 25 minutes. So I don't know how long it would take for me to manually try to sync all like 200 and however many people are in this class. But I contacted Hawks support, and they told me that it was an issue with D2L, so I have to contact D2L support now. So if you see some discrepancies in your grades right now, and you think like, okay, I know I did the section 5.1 homework, why is it showing a 0? Don't worry, I'm working on it, and hopefully I'll have that figured out within the next couple of days. But don't, like I said, the grades are there. They're just not coming from Hawks, so you don't need to go in and redo anything. If you completed it already, it should be in the Hawks gradebook. And even if I have to manually go in and transfer all the grades over, I should be able to get them all done, sometime soon. All right, so I'm going to switch the camera over and we'll get started. All right. So I posted an announcement this morning, just telling you about the due dates that we have coming up. Like I said, this week we're just talking about Chapter 7, but the Unit 5 quiz will cover Chapter 7 and 8. And so it's kind of, like I said, it's kind of far away. The next quiz and the next set of homework will not be due until November 11th. But in the meantime, we do have, I guess I should add that to the beginning of this announcement. We do have a quiz that's due this Wednesday. Is that right? Yes, we have a quiz that's due this Wednesday, October 21st. And that quiz covers Chapter 6, so just Section 6.1 to 6.4. All the people that have taken it so far have done really well on it. So I have all the confidence and faith in you guys that this quiz should be really good for everyone and help boost your grade if you haven't done well in the last couple of quizzes. All right, so let's move over here to our whiteboard. This section is called Sampling Distributions and the Central Limit Theorem. I could just start by reading you the definition of a sampling distribution, but it's even it's kind of complicated even to me when you read it out loud. So, and instead I wanted to share with you this example that the book gives that I think is a good sort of example of what a sampling distribution is. It says, imagine that you've made a big pot of vegetable soup. And the last thing that you have to do, let's say, is just taste it and see if you need to add any seasonings. And the book says, how will you test to see if the seasonings are correct? So of course we're going to, dip a spoon in and taste it. So that would be like our sample. So you dip your little spoon in and taste it. Now you don't need to continue dipping out of the pot of soup until it's all gone. Maybe you take one sample, or maybe you take two samples, and then you should have a good idea of whether or not you need to add seasonings. So that's sort of a metaphor for how sampling distributions work. So we don't need to sample everyone in a population. All we have to do is just take a few samples, and that should give us a good idea of what our population's distribution will look like. All right, so the definition of a sampling distribution says, a sampling distribution is right here. I'm just reading straight off of here, right here. A sampling distribution is the distribution of the values of a particular sample statistic for all possible samples of a given size n. So what that means is that this is just a distribution of different samples. Okay, so you could be measured, say you're going through and you're looking at every single sample of every possible size. So let's say that we're looking at all Americans, and we're going to look at, we're going to sample like 50 people at a time. And maybe we're figuring out their height. So this could be, it says a particular sample statistic. We could be looking at their average height, or we could be looking at the standard deviation of their heights, or the variance of their heights. But the sampling distribution would be made up of all the different samples of size 50. You can choose whatever sample size you want. And then a sampling distribution of sample means this is just a specific definition for when you do a sampling distribution and you figure out what the mean is for each of the samples. It says the sampling distribution of sample means, it's just the distribution of sample means for all possible samples of a given size n. Now, I know that sounds complicated, so let me see if I can do a better job of explaining what this is. So a sampling distribution is created whenever you calculate some particular sample statistic. Like I said, it could be a mean, could be a standard deviation from all possible samples within some population. All right, so say that you start with a population that's any shape. Maybe this distribution is skewed. Maybe it looks like this. Maybe your distribution is kind of skewed, skewed to the right. That means peak will be on the left. Let me try again. Maybe it looks kind of like that. What a sampling distribution means, or what a sampling distribution does, it says if we start with this population here, this skewed population, and we continue to take samples of a certain size, say we take samples of size 10 over and over and over. In theory, if we continue taking these samples until all possible samples have been chosen or selected, then the distribution created from these samples would be normal, or would be symmetric and bell-shaped. So it would look like this. So what that means is that most of them would have, this again is like, let's say we're looking at the sampling distribution of sample means. Most of them are going to have a mean that's here in the middle. It's about average. Some of the samples may have a larger mean. Some of the samples may have a smaller mean. So they would be down here. We're going to learn in just a minute more about the fact that let me start over. We're going to learn more in just a minute about how or why it works that eventually these come out to be in the shape of a normal distribution. But first, we need to look at a couple of important attributes of sampling distributions of sample means. All right, so here are the two formulas that are very important for this section. It's kind of hard to read them, so I'll write them off to the side so that they're a little bit clearer. It says the mean of a sampling distribution of sample means, and it has the symbol there. It's mu sub x bar. So this again is the mean of the sampling distribution of sample means. It's just equal to the population mean. So very simple formula on that one. The next one is a little bit more complicated. It says this is the standard deviation of the sampling distribution of sample means, also called the standard error of the mean. It says the standard deviation of a sampling distribution of sample means, the symbol for that is sigma sub x bar. It's equal to the standard deviation of the population, which is sigma, divided by the square root of the sample size. If you're curious as to why we divide by the square root of the sample size, this is because as your sample gets larger and larger, let's say that you have a sample of 1,000, that's going to make your standard deviation smaller, right? So dividing by something like the square root of 1,000 is going to make the standard deviation smaller. When you divide by a large number, it's going to make that number a lot smaller. So this sort of, I don't want to say penalize, because it's really sort of the opposite of penalizing. It's like rewarding you for taking a larger sample. So the larger your sample, let's write that down here. The larger your sample is, the smaller your standard deviation of sampling distribution will be. So I abbreviated in a couple spots there. So the larger your sample is, so the larger your value of n is, the smaller your standard deviation of your sampling distribution will be. So it's that dividing by the square root of n is really rewarding you for choosing a larger sample, because it's going to make your standard deviation smaller, which is good. You want to have a small standard deviation if you can, because that means that all of your values are close to the mean. All right, so now we're going to get into doing some examples. These are, like I said, the theory behind this stuff is very complicated. If you feel completely lost about what I've said so far today, don't feel bad, because this is very complicated. We're going to talk about this stuff over and over again, so this will not be the only time you hear me talk about this. But even though the theory behind this stuff is very complicated, the actual problems that you're going to see in the homework are pretty simple. So let's look at a couple of examples. It says, find the mean and the standard deviation of the sampling distribution of sample means using the given information. Round to 1 decimal place if necessary. So it gives you the value of the population mean, the population standard deviation, and the sample size. And they're asking us to calculate these two things, the mean of the sampling distribution and the standard deviation of the sample distribution of sample means. All right, so let's write down our formulas. The mean of the sampling distribution of sample means is just equal to the mean of the population. The standard deviation of the sampling distribution of sample means is equal to the population standard deviation, sigma, divided by the square root of n. All right, I'm going to pull up my calculator. That's not my calculator. There we go. Sorry, I was drawing a picture for somebody else back there. All right, there we go. first one, super easy. We don't need to do any calculating here. You just write down what the mean of the population is. It's 39. We don't need to round to 1 decimal place because this is a whole number. All right, for this one, we have the standard deviation of the sampling distribution of sample means is equal to the standard deviation divided by square root of n. All right, standard deviation is 8 divided by square root of the sample size, which is 4. Right, so get your calculator. 8 divided by square root of 4 is 4. We don't need to round there either, since we have a whole number. And that's it. You're done. So that's all you have to do for these. We're going to do one more together. And there's one at the end that's just like this, but it's in the form of a word problem. So we'll do one like that also. All right, so we're going to do one more, and then I'm going to talk about the central limit theorem. All right, so again, same directions. Find the mean and the standard deviation of the sample and distribution of sample means using the given information. Round to 1 decimal place if necessary. All right, so here the mean is, oh, that's supposed to be 75. We'll leave it at 76. It's not a big deal. The mean is 76. Standard deviation is 14. And the sample size is 36. So I had intended to put 75 for the mean there, but it's fine. Not a big deal. All right, so I'm just writing down the two things I'm asked to find. Mu sub x bar and sigma sub x bar. All right, we know that the mean of the sampling distribution of sample means is just equal to the mean of the population. But for the standard deviation of the sample distribution, we have to take the the population standard deviation divided by square root of n. I feel like I've said sample 100 times today. All right, so let's switch to another color. All right, so the mean, again, the mean is just the same as the population mean, so it's just 76. Super easy. Standard deviation, we do have to plug this in our calculator. So that's going to be 14 divided by square root of n, so square root of 36. All right, so 14 divided by the square root. Whoops, wrong button. 14 divided by the square root 36. All right, round to 1 decimal place, so that will be 2.3. Okay, so super easy. Just making sure you know these formulas, and these formulas are on the formula sheet. Let me pull up the formula sheet and see. I haven't put up a practice quiz for this section yet. I haven't written it yet. So that will be coming in the next couple of days. All right, so here they are right here. So you can see I've got the mean of the sampling distribution of sample means and the standard deviation of the sampling distribution of sample means. First two formulas here, so you don't have to have those memorized. But they're pretty easy, so you may just end up having them memorized. All right, so next I'm going to talk for a little bit again, and then we'll do a couple more examples, and then we'll be done for today. So kind of short class today. All right, so this is the most important part of this section, the central limit theorem. It's a very important theorem in statistics. It's a very powerful theorem, and it is very helpful for us as we move forward. All right, and I'll talk about why it's helpful. All right, so it says the central limit theorem, abbreviated CLT. For any given population with a mean of mu and a standard deviation of sigma, the shape of the sampling distribution of sample means will approach that of a normal distribution as the sample size increases. All right, so as you choose a larger and larger sample size, what this says is that your sampling distribution of sample means is going to get closer and closer to a normal distribution. And this next part is very important. It says, this might be something that you want to write on your index card. It says, for this text, we will consider a sample size to be large enough if the sample size is greater than or equal to 30, as is common practice. So this is traditionally and historically accepted in most texts, or in every textbook that I've ever read, that if your sample size is at least 30, so 30 or bigger, then your sampling distribution of sample means is considered normal, which means that it looks like that, symmetric and bell-shaped. And it says, furthermore, the larger your sample size, so if you choose an even larger sample size like 50 or 100, the better your normal distribution approximation will be. Right? So you want to choose as large of a sample size as you can get in practice. So some of the questions that you will see in this section, they will ask you, like the one below here. I'm going to come back and talk about the central limit theorem a little bit more and why it's so important, but let me just show you what type of questions you'll see on the homework about the central limit theorem. It says, can a normal approximation be used for a sampling distribution of sample means from a population with a mean of 58, a standard deviation of 10, when the sample size n is 25? This might sound complicated, but it's actually pretty simple. It says, for this text, we will consider a sample size to be large enough to use the normal distribution approximation if the sample size is greater than or equal to 30. This sample size is not greater than or equal to 30, so we would say no. We cannot use a normal approximation and the reason why, let me scoot this up a little, and the reason why is our sample size n equals 25 is too small. The sample size must be at least 30. Now on the homework, this is a multiple choice question, and I think it says something like, one of the answer choices is no, sample size is not at least 30, or sample size is too small. It may say something like that. All right, so that's the type of questions that you'll see about the central limit theorem. But let me backtrack a little bit and talk about why the central limit theorem is so important. And we'll give you a second to finish writing that down if you're writing it down. All right, so I told you what the central limit theorem is. It says that if you have any population, could be, let's say you might start off with a discrete random variable, maybe a binomial random variable or Poisson random variable. It doesn't matter it doesn't matter what type of population you're dealing with. It says for any given population that has a mean of mu and a standard deviation of sigma, your sample distribution of sample means is going to approach that of a normal distribution as your sample size increases. Right, so that means that your sampling distribution is going to be approximately normal as long as you have a large enough sample size, which we know is at least 30. Now, this is very important and very useful because we know a lot about the normal distribution. We learned in chapter 6 in the last unit that we did that the normal distribution is really easy to use. If you remember, almost all of our questions, we did them the same way. We just went to normal CDF. We plugged in our lower limit, our upper limit, our mean, and our standard deviation, and we were able to quickly calculate areas under the curve. So given that we have all of this information at hand that we already know about the normal distribution, it's very useful for us to be able to say that, that we can approximate this sampling distribution of sample means with the normal distribution as long as our sample size is big enough, because it allows us to use all those nice things that we know about the normal distribution. And this is what I wrote up before class about the central limit theorem. So I'm going to read to you what I wrote. Since we know exactly what the distribution of means will look like. You can take a mean from a single sample and compare it to that sampling distribution. And that's what we're going to be doing in Chapter 8 and in Chapter 10. So we'll take a single sample and we'll compare that to the entire sampling distribution, and we'll be able to answer questions about the likelihood that our sample comes from that sample population. So I'll type that out just in case anybody wants to have that written down. Since we know exactly what the distribution of means will look like for a given population, we can take the mean from a single sample, compare it to the sampling distribution, answer questions about the likelihood that our sample comes from the sample population. So this is another reason why the central limit theorem is so important. So the central limit theorem tells us what the distribution of means is going to look like. It tells us it's going to look like a normal distribution. So since we know that the distribution of means is going to look like a normal distribution, and we know so much about the normal distribution, it allows us to answer questions about the likelihood that our sample comes from the sample population. So those type of questions will be the type of thing that we do when we get to Chapter 8 and Chapter 10. For now, we'll just be learning more and more about the central limit theorem. In Chapter 7, that is. All right, and then I think I have 2 more questions, and then we'll be done for today. This was at the it's at the beginning of my homework set, but I think it depends on yours. It may not be at the very beginning. It says, decide if the statement is true or false. A sampling distribution of sample means has a standard deviation equal to the population standard deviation, sigma, divided by the square root of the sample size. So is that true? Let's write it out and see what it says. Sampling distribution of sample means has a standard deviation. So that's the standard deviation of the sampling distribution equal to the population standard deviation, sigma, divided by the square root of n. And that is true. So this is true. So that was one of our formulas that we learned at the beginning of the class. All right, and then we have one last question to go over. And again, this is that one that I was telling you about at the beginning of class. This is just like what we did at the very beginning of class. It's just a word problem. It says, suppose that a study of elementary school students reports that the mean age at which children begin reading is 5.5 years or 5.5 years, with a standard deviation of 1.1 years. So on average, kids start to read when they're about 5.5 years old, and the standard deviation is 1.1. So if you subtracted one standard deviation, that would be like 4.4 years old. If you added one standard deviation, that would be 6.6. All right, so it says, if a sampling distribution is created using samples of the ages at which 47 children began reading, what would be the mean of the sampling distribution of sample means, rounded 2 decimal places if necessary? Now, typically what you will see done is the first thing you always need to check is to make sure that your sample size is big enough. We know that our sample size has to be greater than or equal to 30. And this one it's 47. So the sample size is big enough, so you can check that off. Now we can go and calculate the sample mean, or excuse me, the mean of the sampling distribution. The formula for that is just the mean of the population. The mean of the population is 5.5. It says round to 2 decimal places. We can just leave it at 5.5. That's fine. Okay. And then last one starts off the same. It says, if a sampling distribution is created using samples of the ages at which 47 children begin reading, what would be the standard deviation of the sampling distribution of sample means, round to 2 decimal places, if necessary? All right, so we're going to write the formula. So sigma sub x bar, which is the standard deviation of the sampling distribution. Formula for that is just the standard deviation of the population divided by square root of n. So standard deviation of the population was, if we scoot back up, oops, I hit the wrong thing, sorry, was 1.1. All right, so that's 1.1. 1.1 divided by square root of the sample size, which was 47. All right, so let's get our calculator. 1.1 divided by the square root of 47. And there's our standard deviation of our sampling distribution. They said round to 2 decimal places, so that would be 0.16. 0.16. And there you go. All right, so we'll talk more about the central limit theorem tomorrow. But like I said, right now, what is most important is that you remember these formulas and you remember things like, for example, how the sample size needs to be at least 30 for us to be able to use the central limit theorem or these little formulas for the mean and the standard deviation of a sampling distribution. All right, I'm going to flip my camera back over. All right, so what we need to be working on this week. Again, if you haven't taken the Unit 4 quiz yet, that's due on Wednesday. So make sure you complete that quiz. And after that, you can get started on the Section 7.1 homework. And like I said, if you're noticing some discrepancies in your grades between Hawks and D2L, just give me a couple of days. I'm working on getting all those grades to sync over. I don't know what the issue is, but I did notice that somehow the auto sync had been turned off. So maybe tonight at midnight, everything will get resynced and everything will be in there like it's supposed to be. But I'm going to try to figure that out today before I leave. But thank you all for coming today, and hopefully I'll see you tomorrow. I'll be covering Section 7.2. Which is, again, just more about the central limit theorem. So in the meantime, you can email me if you have any questions, and I'll see you guys soon. Have a good day.